In this video, I will cover ethers, epoxides, thiols, and sulfides. An ether includes an oxygen atom bonded to two carbon-based groups, and the R groups shown here, they're often alkyl groups, but they can also be aryl groups or vinyl groups, but they cannot be acyl groups. So notice this oxygen's connected to a carbonyl carbon. That's not an ether, that's an ester. However, if we got rid of that carbonyl, that would be an ether. So it needs to be bonded to carbons on either side, but also the group cannot be an acyl group. Ethers are common functional groups in many natural and synthetic compounds. Here is the structure of Prozac, an antidepressant. And notice the ether here. We have an aryl. The benzene ring is a type of aryl group on one side, and here we have an sp3 carbon on the other side. Vitamin E has an ether here, and then morphine also has an ether. Oftentimes, common names are used to name ethers, where you name each R group, arrange them alphabetically, and then end with the word ether. So this would become ethyl methyl ether, and this would become tert-butyl methyl ether. For the IUPAC systematic naming system, the larger R group is the parent chain, and then the smaller R group is the alkoxy substituent. So this ether, for example, you have 1, 2, 3, 4, 5 carbons in the longer chain. So that's the parent, that's going to be pentane. And then you have ethoxy as the alkoxy substituent. Ethers cannot hydrogen bond amongst themselves, so their boiling points are much lower than alcohols of comparable size. So if we look here at ethanol, that has a boiling point of 78 degrees, but dimethyl ether has a boiling point of minus 25 degrees Celsius. Ethers are common solvents used in organic reactions. Diethyl ether is very common, as is tetrahydrofuran and 1,4-dioxane. These have relatively low boiling points, which means they're easy to be removed after the reaction is completed. Also, they're fairly unreactive, so they won't also competitively react with your compounds. Ethers can stabilize metal atoms with a full or partial positive charge, and for this reason, ethers are often used as solvents for Grignard reactions because they stabilize the partially positive magnesium atom in the Grignard. Crown ethers are ethers with a lot of ether functional groups. So for example, this one has 4 different ether groups. This has 5 and this has 6. And this results in especially strong attraction to a metal atom. The way this is numbered is the 12 is the total number of atoms, and the 4 is the number of oxygens. And when I say total number of atoms, I mean carbon and oxygen atoms. We're not including hydrogens in that number. The size of the metal must match the size of the crown to form a strong attraction. So 18 crown 6, for example, is the perfect size for the potassium cation. Crown ethers are often used to help solubilize metal ions because metal ions are not soluble in low polarity solvents. However, if you add a crown ether, it complexes with the metal cation, and then the resulting complex is soluble. So for example, if you have potassium fluoride, the potassium ion can interact and be attracted and stabilized by the crown ether, and then because of that, it will be soluble in benzene. Without the crown ether, potassium fluoride is not very soluble. So which crown ether you want to use depends upon the size of the metal cation. So lithium is very small, so we're going to use the smaller crown ether. Potassium is much bigger, so we want to use the larger crown ether for potassium. It needs to be the right size for the metal ion to fit inside. Industrially, diethyl ether is prepared by the acid-catalyzed dehydration of ethanol, as shown here, and simple symmetrical ethers can be prepared in this way. Perhaps the most famous ether synthesis is the Williamson ether synthesis, and this is a very viable approach for asymmetrical ethers, where the R groups on either side are different from one another. So this is a 2-step reaction. In the first step, you use a base, typically sodium hydride, and that's going to remove the acidic hydrogen off of the OH group. And now you have a nucleophile. Now that nucleophile in the second step is going to do an SN2 reaction. So it's going to attack an alkyl halide, displacing the halogen leaving group to form your ether product. Since this is an SN2 reaction, it has the same limitations that we talked about with SN2 reactions, where it really needs to only be coupled with unhindered alkyl halides. Primary and methyl are the best. So consider these two possible routes to synthesize methyl T-butyl ether. The top route will work because we're going to take the T-butyl alcohol, deprotonate it with sodium hydride, and then do an SN2 with methyl iodide. However, this bottom reaction won't work because here we're using the methanol as the nucleophile after we deprotonate it with the sodium hydride, and then we're trying to attack a tertiary halide, which those do not work with SN2 reactions. They're just too hindered. There's too much bulk around this carbon atom for that nucleophile to actually get in there and kick out the iodide. Recall that oxymercuration demercuration can be used to make alcohols where we put the OH on the more substituted carbon. Well, we can also use this to prepare ethers. It's the same reaction essentially. The only difference is we're going to use an alcohol instead of water. And so we end up adding OR instead of OH to the less substituted carbon. In naming cyclic ethers, so ethers in a ring, the size of the ring determines the parent name. Those are shown here. Oxyranes are more commonly known as epoxides. An epoxide can have up to 4 R groups because each carbon of the epoxide can have 2 R groups attached to it. And epoxides, while they are somewhat unstable, they are found in nature. So for example, here are some pheromones that are found in nature that contain epoxides. There are 2 methods for naming epoxide. One is the oxygen is treated as a side group and 2 numbers are given as its locants. So here we would number the longest chain, which would be pentane in this case, and then we would number from the side that gives the epoxide starting at the lowest possible number, so that would be in this case numbering right to left, and we're going to call the epoxide epoxy with the numbers indicating which carbons are participating in that epoxide, and then we name the rest of the substituents as normal. The second way, which might be easier, is to use oxyrane as the parent name and then number the oxygen as 1, and then you want to number the 2 and 3 such that the lower number would come alphabetically first. So in that case, the 2 is connected to the ethyl groups. Ethyl comes before methyl, so that's why we've numbered it with the 2 carbon here and the 3 carbon here. So this is 2,2-diethyl 3,3-dimethyl oxyrane. Now I would like you to try naming an epoxide of your own creation. Draw any epoxide you would like. I drew one here that has the 3-membered epoxide ring with an oxygen and a methyl and a phenyl ring. Now, using the rules I just told you, see if you can name it, and then you can check it using a feature in ChemDraw. You're going to go up to the top and go to the Structure tab, and then you're going to convert this structure to the name. So you go to Structure, click Convert Structure to Name, and there's the name. So you can check yourself. Now I want you to paste your structure with the name into the chat. Recall that we can make epoxides by reacting an alkene with MCPBA. And you may also recall that epoxidation is stereospecific, meaning if you start with R group cis to each other in the beginning alkene, they are also cis to each other in the epoxide product. Similarly, if they start out trans, they also end up trans in the epoxide product. Epoxides can also be synthesized from halohydrin. So this is a halohydrin, halo because it has a halogen, hydrin because it has an OH group. So in this, we use sodium hydroxide, which is going to deprotonate the acidic H on the alcohol group, and then that will attack the carbon with the bromine, kicking off the bromide in an SN2 fashion. So here is the mechanism. So see, in the first step, we're removing this acidic proton, so the hydroxide is going to grab that. Those 2 electrons stay behind on the oxygen. Now we have an O minus, and that's going to do an intramolecular attack. So it attacks the carbon here, kicking off the bromide to form the epoxide. So, and this is just an SN2 reaction. But notice it's intramolecular. It's happening within the same molecule. Epoxides are useful because we can have a variety of nucleophiles attack them, such as Grignard reagents, hydride reagents, alcohols, and alkoxides. So a ring opening reaction will occur in the presence of a strong nucleophile. So for example, if we have hydroxide, it's going to attack one of the 2 carbons of the epoxide, and then that carbon-oxygen bond breaks and we open up the ring. And then in a subsequent step, we can protonate the formed O- to form this diol product. And the driving force for all of these reactions where we have nucleophiles attacking epoxides is the relief of ring strain, because a 3-membered ring is quite strained. And this is an overview of all the various nucleophiles that can open up an epoxide. So we could have an alkoxide where R is an alkyl group. We could have a cyanide, so that's carbon triple bonded to nitrogen with a negative charge. We could have a thiolate, an SH. We could have a Grignard, and we could have a hydride. For these types of ring opening reactions, they occur via SN2 mechanisms, and the least hindered carbon is going to be attacked by the strong nucleophile. So this carbon has 2 hydrogens on it, so it is much less sterically hindered than this carbon, which has 2 methyls. So the nucleophile is going to attack that carbon and open up the ring. The second step with water is simply going to protonate the O- that is formed. And just like with other SN2 reactions, we will get inversion of configuration. So notice the chiral center here. When the nucleophile attacks, it will attack from a backside attack, and it will open up the ring, and therefore the chirality of that center is inverted. Notice the nucleophile is on a dashed bond, so it's pointing down where this bond was originally pointing up. Now I want you to try to do some reactions where we're adding nucleophiles to epoxides. So in all of these, we have strong nucleophiles, and so it's going to add to the less hindered carbon. So for example, with part A, the nucleophile is phenyl Grignard. pH stands for phenyl, which is a benzene ring. So in this, the benzene ring is going to add to the less hindered carbon of the epoxide. And when it does that, it opens up the epoxide, which then in the second step gets protonated by the acid. So now try parts B through F on your own. Pick any of the reactions, draw what the product is, take a picture of what you drew, and paste it into the chat, along with some explanation of how you got to that product. So in part B, the nucleophile is CN, or cyanide, carbon triple bonded to nitrogen with a negative charge on the carbon. In part C, the nucleophile is the S-methyl. Me stands for methyl. So that's a sulfur bonded to a methyl with a negative charge on the sulfur. In part D, the nucleophile is the lithium aluminum hydride. So it's going to be H- is the nucleophile. In part E, NaOET stands for sodium ethoxide. ET is short for ethyl. So the nucleophile there is an oxygen with a negative charge, and the oxygen is bonded to an ethyl group. And then part F, we have a lithium aluminum hydride again, where the hydride is adding as the nucleophile. So try any of these, try all of them if you want, but pick one of your products drawn, take a picture of it, and paste that into the chat along with an explanation of how you got to that answer.